All right, team. Here's our first example. This is 4.3, video B, optimization. And the story is a farmer's field is fenced as shown. And I guess I should say that this is a rectangular field. And we should note that the fences are here, along the bottom, along the side, across the top, as well as that length there. What dimensions maximize the area if they have only 300 feet of fence? And, you know, we have this step-by-step process, and step one was to make a picture, and the picture is made for us. Step two, what are we trying to optimize here? And we're trying to certainly optimize the area. It says so, maximize the area. And step three will be that we have to make some area equation. And the area of a rectangle, this is a geometric formula that we should know, x times y. Now, in the previous video, I said, hey, we have one of two possibilities when we make the equation. We're either going to have one unknown, and then we're ready to go, or we're going to have two. And in this case, we have two unknowns, and so I need to make a constraint equation. And a constraint is some limiting factor. So the limiting factor here is that 300 feet. Now, how does that 300 feet relate to our picture? Some of you are saying, oh, well, 2y and 2 x's. But you're not entirely correct. I certainly have two x's, an x there and an x at the top. Those are fence of length x. But I have 1, 2, and then a third of these y lengths. Now, we're not quite done. We have to take this, solve for a variable, and substitute it back into our previous relationship. And I think that while we could solve for either, I like dividing by 2 more than I like dividing by 3. And so let's solve for x by stating that 150 minus 1.5y is equal to x. Yeah. Let's make that substitution happen. And now we're going to have the area as a function of y. And to substitute whenever I have x in my previous formula, I'm going to write here 150 minus 1.5y times y. I'm going to do a little bit of housework here. And so 150y minus 1.5y squared, and we have our relationship. This is good news because now I have to find my critical points by taking the derivative. A prime of y gives us 150 minus 3y. Not too bad. We'll set that equal to 0. I should probably say that we're now on step 5. And we solve and we see that 50 is equal to y. Now, many of you are like, okay, we're done. We can get the x value and we're through. But unfortunately, we still have to justify this thing's existence as a global max, that the area is going to be maximized. And so what we're going to do is we need to find the domain and our critical points. So the domain in this case is going to come from the constraint equation right here. And if I look at this, could y be equal to 0? And the answer is sure. I would have the worst rectangle's area possible. The area would be 0, but that would mean that x would be equal to what? I would take the 300 feet of fencing. That would be 0. This would be 0. That would be 0. And I'd use all 300 feet, and so x would be 150. And we can see that here. If I put 0 in for y, x is 150. Now, I don't really care about the x value. All I'm concerned about the y value. But now I can say, hey, suppose x was 0. How long would y be? And I know that you know we have 300 feet and I have 3 lengths of y. So y would be equal to 100. Now, we could also do that here. If x is 0, we could see that y is 100. And these are all in feet. And so my domain is 0 to 100 feet. Awesome. Now that we have the rock, what are we going to do with it? We're going to plug these things back into the original relationship that we constructed in terms of y. So a of 0 gives us what? Well, we can see 150 times 0 minus 1, oh, that's going to be 0, which is exactly what we said would go down. When the height is 0, there's no area. A of 50, we can plug that in, and I should probably say that that's square feet, but using my TI-80 Awesome, 150 times 50 minus 1.5 times 50 squared, and we get 3,750 square feet. And then finally, A of 100, and this is a little bit trickier to see, but if I break this up, y times y, 1.5 times 100 is 150. 150 times 100 minus 150 times that remaining y, which is 100, that'll be 0 square feet as well. Here, we've tested all of our values, and that's where the maximum area occurs. Now, the one thing we haven't done is we haven't really answered the question. They wanted to know what dimensions maximize the area. We have the maximum area. We have the y dimension, which is 50. How do I get the x dimension? Oh, I can plug it back into my constraint equation. So 150 minus 1.5 times 50 equals x. And it turns out that x is equal to 75. And we're done. When x is 75 feet and when y is 50 feet, we maximize the area of the field. Okay, more problems are coming up. Stay tuned.